Good morning, everyone. I'm Dr. Anshu Sharma, Assistant Professor, Department of Physics, Maharaja Agarsen University. Today, I'm going to give presentation on the topic Introduction to Superconductivity. Before explaining superconductivity, let me first explain in electrical resistance. Electrical resistance is the restriction to the passage of charge. As we know that electrons cannot travel from a direct route from one terminal to another in an electric circuit, but it's a zigzag path that results from the countless collision with the fixed atoms in the conducting material that hinders the movement of electrons. Therefore, electrons have resistance. The resistance to the flow of charge is comparable to the flow of water through the pipe, that is frictional effects between the water and pipe surfaces, as well as the obstacle produced by the path. And this is the resistance that hinders the flow of water. Factors affecting the electrical resistance are total length of the wire, cross-sectional area of the wire, material of the wire, temperature of the conducting material. Resistance R is directly proportional to the total length of the wire and inversely proportional to the cross-sectional area of the wire. Resistance is measured in ohms. Now, what is superconductivity? When we classify the materials, we classify them as insulators, semiconductors, and conductors. Apart from these materials, we also have another type of material known as superconductor. Superconductors are the materials which possess the superconducting phenomena. So superconductivity is the property of some materials to conduct direct current with almost zero resistance. Or we can say certain materials' resistance disappears at certain low temperature, causing them to become superconductors. Superconductors come in variety of forms that include materials, those made of aluminum, magnesium diboride, deuterium, barium, etc. When certain materials are heated below their critical temperature, they shows the phenomena of superconductivity. Origin of superconductivity. In 1911, while studying the properties of material at very low temperature, the Dutch physicist Camerlingons discovered that the electrical resistance of mercury goes to zero below 4.2 Kelvin. The temperature at which resistance suddenly falls to zero is known as critical temperature. The cooling of the material can be achieved by liquid nitrogen or liquid helium for even more lower temperature. Next is Misner effect, or we can also call it a perfect diamagnetism. Misner effect is the expulsion of magnetic field from interior of a material that is in the process of becoming a superconductor, that is losing its resistance to the flow of electrical currents when cooled below a certain temperature known as transition temperature, usually close to absolute zero. Here in this diagram, we can see for normal conductor, temperature is greater than critical temperature, and the normal conductor can pass all the magnetic field to them. For superconductor, temperature is less than critical temperature and it can expel all the magnetic field. In 1933, German physicist W. Misner and R. Oschenfeld first identified the Misner effect, which is characteristic of all these superconductors. According to this Misner effect, magnetic flux density B does not exist in the superconductor. Therefore, B equal to 0 and H equals to minus M. Therefore, susceptibility chi equals to minus M over H, which is negative. This is the case of perfect or ideal diamagnetic material. Now, types of superconductors. There are two types of superconductors. They depends upon their behavior in an external magnetic field. So let me first explain type 1 superconductor. These types of superconductors lose their superconductivity very simply, very easily when it is placed in the magnetic field at the critical magnetic field. After that, it will become like a conductor. These types of superconductors are also known as soft superconductors due to the reason of loss of superconductivity. And these superconductors obey the Meissner effect completely. And this kind of superconductors include basic conductive parts, and these are utilized in different fields from electrical cabling to microchips on the computers. Examples of this type of superconductors are lead, mercury, zinc, and aluminium. Next is type 2 superconductors. Type 2 superconductors are those superconductors that lose their superconductivity gradually but not easily or abruptly when placed in an external magnetic field. From the graph of intensity of magnetization versus magnetic field, when the type 2 superconductor is placed in magnetic field, it gradually loses its superconductivity. Type 2 superconductors start to lose their superconductivity at the lower critical magnetic field Hc1 and completely loses their superconductivity at the upper critical magnetic field Hc2. The state between lower critical magnetic field Hc1 and upper critical magnetic field Hc2 is known as vortex state, or we can say the mixed state. After Hc2, the type 2 superconductor will become a normal conductor. Type 2 superconductors are also known as hard superconductors because of the reason that they lose their superconductivity gradually but not easily. Type 2 superconductors obey Meissner effect but not completely. Type 2 superconductors are used for strong field superconducting magnets. Example of type 2 superconductors are NBN, BA, BI, 3, etc. Now next topic is BCS theory. The American scientist John Burdeen, Leon N. Cooper, and John N. Schiffer created the BCS theory in 1957 as a complete explanation for the behavior of superconducting material. And this theory explains only type 1 superconductor. Their last names used as the initial of BCS theory, Burdeen, Cooper, and Schiffer received the Nobel Prize in 1972 for the development of the theory of superconductivity. A key conceptual element in this theory is the pairing of electrons close to the Fermi level into Cooper pair through interaction with the crystal lattice, and this pairing results from a slight attraction between the electrons related to lattice vibrations. The coupling to the lattice is called phonon interaction. The BCS theory relies on the assumption that superconductivity arises when attractive Cooper pair interaction dominates over the repulsive Coulomb force. A Cooper pair is a weak electron-electron bound pair mediated by a phonon interaction. An electron in the cation lattice will distort the lattice around it, creating an area of greater positive charge density around itself. Another electron at some distance in the lattice is then attracted to this charge distortion phonon, the electron-phonon interaction. The electrons are therefore indirectly attracted to each other and form a Cooper pair. An attraction between two electrons mediated by lattice, which creates a bound state of the two electrons. Next is formation of Cooper pairs. How Cooper pairs are formed. When a metal is cooled to the critical temperature, electrons in the metal form Cooper pairs. Cooper pairs are electrons which exchange phonons and become bound together. Bound electrons behave like bosons. Their wave function do not obey Pauli's exclusion principle, and therefore they can all occupy the same quantum state. According to BCS theory, bound photons have lower energy, which prevents lattice collisions and eliminates resistance. As kT less than binding energy, then current can flow without any dissipation. Now, next is properties of superconductors. Superconducting materials shows some extraordinary properties which make them very important for modern technology. Firstly, critical temperature, transition temperature. The temperature below which material changes from conductors to superconductors is called critical temperature or transition temperature. The transition from conductors to superconductors is sudden and complete. Zero electric resistance or infinite conductivity. In the superconducting state, the material has zero resistance. When temperature of the material is reduced below critical temperature, its resistance suddenly reduces to zero. Example is mercury, which is a superconductor that shows zero resistance below 4.2 Kelvin. Next is expulsion of magnetic field, which is Misner effect. Below critical temperature, superconductors do not allow the magnetic field to penetrate inside it. This phenomena is called Misner effect. The critical magnetic field. The certain value of magnetic field beyond which superconductors return to conducting state is called critical magnetic field. The value of critical magnetic field is inversely proportional to the temperature. As temperature increases, superconductivity. Applications of superconductors. Superconductors have various applications just like in science, medical, transportation, industrial, and energy sectors. Superconductors are used in particle accelerators, generators, transportation, computing, electric motors, medical, power, transmission, etc. Superconductors are primarily used for creating powerful electromagnets in MRI scanners. These conductors are used to transmit power for long distances. They are used in memory or storage elements. Future possible applications of these type of materials involve high performance smart grids, electric power transmission, transformers, electric motors in vehicles like maglev trains, magnetic levitation devices, superconducting, magnetic refrigerators, etc. Thank you.